Welcome to the Deep Dive, the place where we take those overwhelming stacks of research, the technical documents, and all the insider notes, and really just boil them down to the foundational knowledge you need to be truly well-informed.
Today, we are deep diving into, well, the invisible engine of the internet, Linux. And this isn't just about operating systems. It's about infrastructure, it's about philosophy, and the legal framework that runs something like 90% of the cloud and billions of devices you use every day.
Often without ever even seeing a screen.
Exactly.
Without a screen.
I mean, if you're listening to this right now, whether you're streaming it to a smart device or it's coming through a mobile carrier or you're pulling data from a major cloud host, that entire digital chain is pretty much resting on Linux.
It is. It runs the data centers, the servers, the routers, probably your smart TV. The ubiquity it's kind of shocking, but the core concepts get so wrapped up in technical jargon.
And that's what we want to cut through. So our mission today is to give you a confident, comprehensive understanding of this whole world. We're going to untangle the crucial differences between the Linux kernel and a full distribution. We'll get into the business models built around open source, and maybe most importantly, we're going to clarify what free actually means here, because it is not about price.
It's about freedom.
It is. And this knowledge is, it's fundamental for anyone in tech, or really anyone just concerned about digital security and privacy these days.
Okay, let's get started. I think we have to begin by defining our terms right at the very center of the system. We need to understand exactly what Linux is, because if you just assume it's an operating system like Windows, you're already missing the point. So when people first get into this, they might ask, is Linux just like Windows or Mac OS? And the answer, as our sources really hammer home, is that you need to kind of refine your thinking there.
You absolutely do. I think the single most important takeaway from this whole segment is that Linux itself is fundamentally the kernel, just the kernel. It's the core, the central piece that acts as the ultimate go-between for the software and the physical hardware.
Okay, so it's not the flashy icons, not the windows, not the mouse cursor. It's the resource broker. What are the specific jobs of this kernel, this broker?
The kernel has absolute authority over the machine's resources. It manages the hardware, the CPU, the hard drive, any peripherals you plug in. Critically, it manages memory allocation, making sure programs don't step on each other's toes.
So they stay in their own little sandboxes.
Exactly. And it handles process scheduling. So it decides which program gets to use the CPU and for how long. It's the operating system's brain. And this brain was, famously, the initial project of Linus Torvalds way back in 1991.
But that brain didn't just appear out of nowhere. It has a parent, right? Or at least a really powerful influence in computing history.
Oh, for sure. That's the Unix connection. Linux is very, very heavily inspired by Unix. It inherits all its core design principles, like the everything is a file philosophy, the modular approach, the powerful command line. The goal was always to provide a stable, multi-user, multitasking system, but, and this is the key, to do it as a free and open alternative to the proprietary, really expensive Unix systems that were all over universities and big companies back then.
And that decision to make it open, that was revolutionary. It completely changed the ownership model.
It really did. The defining feature of Linux is that it is community-driven. There's no single company that owns the Linux kernel. It's developed and maintained by this global team of contributors. You have individual hobbyists, but you also have developers paid by giants like Red Hat, Google, IBM.
All working on the same core project.
All working together. This decentralized, transparent, and collaborative model is what's allowed it to grow and adapt and stay so resilient for, over 3 decades now?
You know, a fair question might be, doesn't relying on a massive global community introduce more risks, maybe slower decision-making compared to a single company that can just dictate changes?
That's a great question, and it's a common critique. But the reality is often the exact opposite. Decision-making for huge architectural changes can be slower, you're right, because it needs consensus. But that whole process is transparent.
And for security.
For security, the principle of many eyes make all bugs shallow really seems to hold true. When a bug is found in a closed-source system, only the vendor's internal team can even look at it. In Linux, a critical vulnerability is suddenly visible to thousands of experts all over the world.
Which leads to faster patching.
Much faster patching, and usually a much higher quality review of that patch. The community structure is its greatest strength, and it's also its own built-in audit mechanism.
Okay, so if the kernel is just the engine, what's the actual thing we download and install on a computer?
That is the Linux distribution. The kernel needs context to be useful. A distribution takes the Linux kernel and bundles it with all the other essential stuff. system libraries, utilities, often the tools from the GNU project, which is why you hear the term G in Linux.
Which is the more technically accurate term.
It is, and it also includes applications and, this is crucial, a package management system. The distribution is the complete, ready-to-run vehicle tailored for a specific need.
I like that. The kernel is the engine. The distribution is the entire vehicle. Maybe it's a sports car, maybe it's a truck.
It's a perfect analogy, and it leads right into our next point.
Why?
Why are there so many of these vehicles? Why are there hundreds of different Linux distributions?
Yeah, it can be really overwhelming for a newcomer. Why not just standardize on one perfect OS?
Because there's no such thing as a single perfect environment. The reason you have so many distributions is because of different goals, different target users, and different operating environments. A server that's handling 1 million website requests at once has completely different needs than, say, a graphics workstation or a laptop for penetration testing.
Our sources do a good job of structuring this chaos. They break it down into 3 tiers based on goals. Let's start with the big one, the one that prioritizes corporate stability, enterprise grade.
Right. Enterprise users are all about stability, long-term predictability, and reliability. Downtime or some unexpected software change costs them a ton of money. So these distributions, like RHEL, that's Red Hat Enterprise Linux, or ECC Linux Enterprise Server, Debian, and Ubuntu LTS, they all make a very conscious choice to use older, incredibly well-tested versions of software.
Wait, hold on. If they're running old software, how do they deal with modern security threats? That sounds like a huge risk.
It would be, but this is where the concept of backporting comes in. It's a non-negotiable business practice for them. Instead of upgrading a critical piece of software, let's say the Apache web server, from version 2.4 to 2.5, which could introduce new bugs.
And force the client to retest everything.
Exactly. Instead of that, the maintainers take just the security fix from the newer version and they manually apply it to the older, stable code base they're already using.
So they get the security without the instability of a major feature upgrade.
Precisely. The enterprise is paying for that guarantee. They're paying for the labor-intensive work of backporting. That is the core value of a distribution like RHEL.
Okay, so moving down to the middle tier, we have the consumer-grade distribution.
This tier is all about balancing stability with new features. If you're running Linux on a brand new laptop, you need support for the latest graphics cards, the newest Wi-Fi chips. That means you need newer kernels and drivers.
So this is for the average desktop user.
Right. Distributions like Fedora or the non-LTS versions of Ubuntu are designed for that. They give you a more up-to-date experience, and you just accept that the software might be slightly less battle-tested than what the big enterprises are using.
And finally, the third tier for those who like to live on the edge. The experimental or hacker distributions.
These are for users who need the absolute bleeding edge of software, or they have really niche requirements. They often use a rolling release model.
What does that mean, rolling release?
It means the system is just constantly updated. As soon as a new package is ready, it gets pushed out to you. There are no big version 10 or version 11 releases. It just rolls.
Which requires a lot of skill to manage, I'm guessing.
It does, because the system will occasionally break. You have to know how to fix it. We're talking about distributions like Arch Linux, which is famous for its complexity, but also its simplicity, or Gentoo, where you often compile software from source. And of course, specialized tools like Kali Linux for security testing.
The fact that these all have common origins brings us to the distribution family tree. And this isn't just a cute analogy. Understanding it actually determines how you manage the system day to day.
The family tree is key. It defines the fundamental architecture, specifically the package format and the package management system. This is how you actually install software.
So let's break down the big families.
You can start with the Debian family. This is a huge one. It includes Debian itself, Ubuntu, Linux Mint. Their shared DNA is the use of the DEB package format, and they all use tools like dpkg and, more commonly, apt.
And then you have the other huge branch of the tree, the Red Hat family.
The Red Hat family is defined by the RPM package format. And this group has a really interesting dynamic. You have the commercial backbone, RHEL. Then you have Fedora, which acts as the upstream proving ground.
The test bed.
The test bed, exactly. New features, new ideas, they all get tested extensively in Fedora. Once they're stable, they get pulled into the paid enterprise product, RHEL. And historically, you had CentOS, which was a community rebuild of RHEL's source code, giving you enterprise stability without the paid support.
That relationship has changed a bit recently with CentOS Stream, but that's the traditional lineage.
And we can't forget the SES family.
Right. SUV is a big player, especially in Europe and in the enterprise world. You have SE Linux Enterprise Server and then the community version, OpenSesus. They also use the RPM format, but they have their own specialized configuration and management tools on top.
These divisions aren't just technical, they reflect different philosophies, which I know we'll get into later. But for now, let's pivot from the desktop and the server to where Linux is, well, truly hidden and completely dominant.
If you only think of Linux as a server OS, you're missing the vast majority of where it's used. Its dominance in embedded systems is just profound.
So define embedded systems for us. An embedded system is basically a computer with a very specific job. It's a combination of hardware and software built for a highly specific, limited function inside a larger system. They are purpose-built computers.
So like the little computer in my router, or my smart TV, or the infotainment system in a car.
All of those. Your microwave, advanced medical devices, they are all computers, but they only do one or two things.
Why does Linux always win in this space? Why not something simpler?
Three big reasons: customizability, a lightweight footprint, and cost. Because Linux is open source, a manufacturer can just strip the kernel down to the absolute bare minimum. They only include the code they need for that specific device.
Which means they can use cheaper hardware.
Exactly. It dramatically reduces the hardware requirements, lowers the cost of the device, and crucially, they don't have to pay any licensing fees for the billions of units they're shipping.
And the most famous example of this customized Linux kernel is in pretty much everyone's pocket.
Android. Yeah. While Android is heavily customized, with its own runtime and everything at its core, it's based on a modified Linux kernel.
Yeah.
And here's an important distinction. The AOSP, the Android Open Source Project, is free and open. But the Google apps, the Play Store, Gmail, Maps, those are proprietary and require a license from Google.
That's a great distinction to make. Another key example, kind of the poster child for accessible embedded development, is the Raspberry Pi.
The Raspberry Pi is a fantastic tool. It's a tiny, low-cost computer that really popularized prototyping for hobbyists and students. Its key feature is that row of GPIO pins, general-purpose input-output.
Which lets you connect it to the physical world.
Exactly. You can control motors, read sensors, blink LEDs. The main OS for it is Raspbian, now called Raspberry Pi OS, which is a Debian derivative that's been optimized specifically for that low-power ARM hardware.
And finally, the biggest game in town, where Linux is handling just unbelievable amounts of work. The cloud.
The cloud is built on Linux. Modern digital commerce runs on Linux. It dominates servers, data centers, and all the major cloud providers. If you look at Amazon AWS, Microsoft Azure, Google Cloud, the default and most used virtual machines are almost all Linux distributions like Ubuntu or Red Hat.
What makes it so perfect for that high-pressure environment?
It's a combination of everything we've been talking about. Unmatched stability. These systems can run for years without a reboot. Security, because the open source model means faster patches. Flexibility, you can scale it up or down instantly. And of course, cost effectiveness. When you're spinning up thousands of virtual machines, not having to pay for an OS license translates into billions of dollars in global savings.
That stability and efficiency is why all those cloud giants invest so much money back into Linux kernel development.
It's in their best interest too.
Okay, so if Linux is the engine of the internet, we now need to look at how we fuel it. How is the software managed, distributed, and actually used within this huge, diverse ecosystem? Let's move on to the packages and programs that bring it all to life.
You know, one of the biggest mental hurdles for new Linux users is getting away from that idea of just downloading random .exe files off some website. That's a fundamentally insecure way to manage a computer.
So let's unpack the Linux way, which is centralized software management through a package system.
Right. The core idea is that all software is distributed in these things called packages. A package isn't just the program, it's a very structured archive. It contains the application itself, all its supporting files, crucial version information, and detailed instructions for the system on how to install it, configure it, and just as important, how to remove it cleanly.
And the big benefit here is consistency and, most of all, security.
Absolutely. The advantage of centralized software management is that all your software comes from trusted repositories. These are maintained by the distributions vendor or its community. This ensures the code hasn't been tampered with, and it guarantees that all the dependencies, the other little bits of software your program needs to run, are handled correctly. It maintains overall system stability.
We mentioned the packaging war earlier, which is really defined by that family tree. Let's just reinforce the tools that go with the two main package formats.
On one side, you have the DEB format, that's for Debian, Ubuntu, Mint. The low-level tool is dpkg, but what you'll actually use on the command line is apt-get, or the newer, friendlier apt. These systems build what's called a dependency tree, so they automatically pull in all the other libraries you need when you install something.
And on the Red Hat side of the family.
That's the RPM format. The low-level tool is RPM, and the management systems were historically Yum, and more recently, DNF. DNF is known for being much faster and better at handling those complex dependencies. The key takeaway is, if you know the family, you know the command you need to use.
There's a really important detail when you're removing software that I know system administrators love. The difference between just removing a package and totally purging it.
This is a classic admin choice. If you run a simple remove command, say DNF remove Firefox, the package gets uninstalled, but the system deliberately keeps the configuration files. This is really handy if you think you might reinstall it later, because all your settings will still be there.
But sometimes you want a completely clean slate, right? Especially if a config file gets corrupted.
Then you need the more aggressive command. On a Debian-based system, that would be apt-get purge package name. Purge removes the package and all of its associated configuration files. It's a total clean removal. That level of fine-grained control is really a signature of the Linux command line.
Okay, let's move from the system itself to the applications. We said before that Linux is a perfectly good daily desktop OS. What's out there for the user who needs to, get actual work done?
The open source world has a really robust set of alternatives. The standard bearer for office productivity is LibreOffice. It gives you the whole suite. Writer for documents, Calc for spreadsheets, Impress for presentations, and more.
And the file format they use is actually a huge philosophical win for open technology everywhere.
It really is, and it's a concept people should know about. The Open Document Format, or ODF. ODF isn't just some file format. It's an ISO standard. Because it's an open, globally recognized standard, it guarantees that your documents will be readable forever. It prevents any single company from locking your data into their proprietary format.
So I can switch my Office suite or my whole OS in 20 years, and my data is still accessible.
That's the promise. That guarantee of data portability is a massive practical and philosophical advantage.
Beyond Office work, the open source Creative Suite is also incredibly impressive. It gives the big proprietary tools a real run for their money.
For sure. In 3D modeling and animation, you have Blender. It's now used in major film productions. And you can even use it to prep models for 3D printing. For photo editing, there's GIMP, the GNU Image Manipulation Program. It's incredibly powerful, though it's known for having a bit of a steep learning curve compared to something like Photoshop.
And for vector graphics, like logos and diagrams.
That would be Inkscape. It uses the SVG format by default, which is perfect for anything that needs to be scaled up or down without losing quality. And then there are even these more esoteric command line tools that have huge industrial uses.
Like ImageMagick.
Right, ImageMagick. It sounds simple, but it's this incredibly powerful command line tool for converting and processing thousands of images at once. You can use a single command to create a PDF from a folder of images. It's a perfect example of the power of scripting in Linux.
But let's be honest, the strongest use case for Linux isn't the desktop, it's the back end. Let's talk about its server dominance.
The internet basically runs on the LMP stack. That's Linux, Apache, MySQL, and PHP Python Perl, or the newer LEMP stack, which swaps in Nginx for Apache. These are the programs that host the world's websites. Apache and Nginx are the web servers handling millions of requests every second.
And the databases behind them.
The two big open-source relational databases are foundational. You have MariaDB, which is a high-performance fork of the original MySQL, and then you have PostgreSQL, which is famous for its robustness and strict adherence to SQL standards. These free, reliable, high-performance databases are a huge reason for Linux's dominance.
Since we're on resource sharing, we have to talk about how Linux shares files across a network. There's a clear split between how it talks to other Linux machines and how it talks to Windows.
Right. Internally, in a pure Linux or Unix environment, the tool is NFS, the network file system. It's super efficient for that ecosystem.
But in the real world, you have to talk to Windows machines.
And that is where Samba becomes absolutely essential. Samba is the software suite that lets Linux systems interoperate seamlessly with Windows. It handles file and printer sharing, and in more advanced setups, it can even let a Linux server act as an Active Directory domain controller, bridging those two completely different worlds.
You mentioned MariaDB was a fork of MySQL. This idea of the fork is so central to open source, and the story of OwnCloud and Nextcloud is a perfect example of the politics behind it.
It's a great case study. Both OwnCloud and Nextcloud are self-hosted file-sharing services, kind of like your own private Dropbox. Nextcloud is a very successful fork of OwnCloud.
So what was the disagreement that led the Nextcloud developers to just branch off and start their own thing?
It wasn't purely technical, it was really about business strategy and community involvement. The OwnCloud company was pursuing a model where some of the best enterprise features were kept proprietary and behind a paywall. The developers who started Nextcloud felt that this was creating too much friction with the open source community.
So the fork was driven by a desire to keep everything open and community focused.
Exactly. Nextcloud's new direction was to build a fully open ecosystem, integrating things like video conferencing right into the core product. The fork wasn't malicious, it was the open source license working as intended. It gave developers the freedom to take the code in a direction they felt served the users better.
The strength of Linux for administrators lies in these tools, but also in the absolute bedrock of internet communication.
Oh, absolutely. Linux is an admin's dream. It's packed with high-quality tools for remote administration, and it all relies on the fundamental plumbing that admins need to know inside and out. DHCP, which automatically assigns IP addresses on a network, and DNS, which translates the domain names you type into your browser into the numerical IP addresses computers need.
Let's pivot to development. Because Linux is the default for so many programmers, we should distinguish clearly between the two major types of programming languages they use.
Right. When you write code, it has to be turned into instructions a computer can understand. We basically divide this into two camps: compiled languages and interpreted languages.
Let's start with compiled, like the C language.
In compiled languages like C or C++, the source code you write is run through a program called a compiler. This translates the entire program into a machine-readable, executable file before you ever run it. The big benefits are speed. The machine doesn't have to translate on the fly, and you often catch errors early during that compilation step.
So you compile first, then you run the result. What about interpreted languages?
In interpreted languages like Python, PHP, or the all-important shell bash scripting used everywhere in Linux, there's no separate compilation step. The source code is read and executed line by line at runtime by an interpreter. It might be a little slower, but it's much more flexible, easier to test quickly, and it's perfect for automation and web development.
This inherent power and flexibility, plus the ability to fork and share, brings us right to the philosophical and legal bedrock of this entire world, the definition of free.
The entire open source world revolves around this one, often confusing word: free. And as we said, the sources are all adamant that this is about ethics, not about price.
And our sources also emphasize that open source and free software, while related, are actually two distinct movements. What's the fundamental difference we need to understand here?
Open source is the pragmatic technical movement. It just means the source code is available, you can study it, find bugs, improve it. It emphasizes a superior way of developing software. Free software, which is championed by the Free Software Foundation, FSF, is the ethical and philosophical movement.
It's about freedom of expression, but for code.
Exactly. It's all about the user's rights. The key distinction is that free means freedom, or libre, as in Spanish, the freedom to control your own software and your own computing.
And to make that crystal clear around the world, there's an acronym that includes that Libre part.
That's FLOSS, Free, Libre, and Open Source Software. By using Libre, we just remove the price ambiguity of the English word free and make it clear we're talking about the 4 essential rights defined by the FSF.
These ideas only matter if they're protected by law. So this brings us to the legal framework. Licenses. You can't just throw code online and say, do whatever you want with it.
That's right. Open source software is very pointedly not unlicensed. The license is the foundation. It provides the legal clarity everyone needs. It defines the rules, how it can be used, how it must be shared, and it protects against someone taking the code and making it their own proprietary product.
So let's detail Richard Stallman's 4 essential freedoms, the checklist for software to be considered free.
They're numbered 0 through 3. Freedom 0 is the right to run the program for any purpose you want. Freedom 1 is the right to study how it works and change it to do what you want, which of course means you need the source code.
Makes sense.
Freedom 2 is the right to redistribute copies so you can help your friends. And Freedom 3 is the right to distribute your modified versions back to the community so everyone can benefit from your changes.
And Freedom 3 is what legally guarantees the fork, the ability to take the code in a new direction, just like we saw with Nextcloud.
It's the ultimate insurance policy. If the original authors go in a direction the community hates, the community can legally take the code and continue it themselves. These freedoms are protected by two broad types of licenses, copyleft and permissive.
Copyleft is the viral one, the one that ensures freedom keeps spreading.
That's a great way to put it. Copyleft, which is embodied by the JNU General Public License, GPL, is designed to fiercely protect those four freedoms. It requires that any modified versions of the software must also be released under the same copyleft terms.
So you can't lock away the improvements.
You can't. The whole point is to prevent a company from taking open source code, improving it, and then making those improvements proprietary. It protects the future freedom of the software.
In contrast, you have permissive licenses. These are more laissez-faire.
Exactly. Licenses like the BSD or MIT licenses are permissive. They let you reuse the code, modify it, and even include it in a completely proprietary closed-source product. All you have to do is keep the original copyright notice. They maximize reuse, but they don't guarantee the freedom of whatever you build with it.
We have to talk about the evolution of the GPL, specifically from version 2 to version 3, because it really shows how this philosophy has to adapt to new technology.
GPL v2 is the classic.
Right.
It's still used by the Linux kernel itself, and it was incredibly effective when it was written. It focused on protecting software freedom when you distributed the software. If you gave someone the program, you had to give them the freedoms. But the world changed.
What were the new threats that GPL v2 couldn't really handle?
There were three big ones that emerged in the early 2000s. First, companies were using GPL code to build DRM, digital rights management, to lock down media. Second, there was the rising threat of software patents. And third, there was hardware restriction, or what became known as anti-TiVoization.
Let's drill down on that. What was the problem with TiVo?
The issue was devices that used GPL software, but their hardware was designed to stop the user from running modified versions of that software. TiVo was the poster child. The manufacturer would release the source code, which complied with GPL v2, but the hardware would cryptographically check the software signature. If you compiled your own modified version, the device would just reject it.
So you had the freedom on paper, but not in practice. So GPL v3, released in 2007, stepped in to close that loophole.
Precisely. The anti-TiVoization clause in GPL v3 specifically says that if this software is on a consumer device, the vendor has to give you the information and keys you need to install and run your own modified versions on that hardware. It protects the physical reality of Freedom 1.
Beyond the main GPL, there are other specialized copyleft licenses for specific situations.
The ecosystem got very specific. You have the LGPL or lesser GPL, which is mainly for libraries. It's a weak copyleft. It lets proprietary software use the library. But if you make changes to the library itself, you have to share those changes.
And then there's the really strong one designed to counter the cloud services model, AGPL.
The Affero GPL, AGPL, is a critical response to the rise of SaaS. A company could take GPL code, run it on a server, and never distribute the software, so they never had to share their changes. The AGPL closes this loophole. It says the requirement to share source code is triggered even when the software is just used over a network.
So it forces SaaS providers using AGPL code to contribute their improvements back.
It does. And finally, for content, you have the FDL, the Free Documentation License, which applies copyleft to manuals and docs. And for creative stuff text, images, we have the Creative Commons CC licenses, which give you a menu of options, like BY for attribution, SA for share-alike, which is like copyleft, ND for no derivatives, and NC for non-commercial use only.
This all brings us to the big financial reality check. If the code is free and the license says you have to share it, how do billion-dollar companies like Red Hat and SUC even exist?
And this is where we really underscore the point. Open source and profitable business are not opposites, they are symbiotic. No one is selling the code. They're selling trust, time, and service.
So the main strategy is selling expertise, not the software itself.
Precisely. It's support and services. A big company with a critical RHEL server farm isn't vouching for the code they could download for free. They're paying for a service contract that shifts the risk. They're paying for guaranteed patches, certified hardware, consulting, and the promise that if something breaks, a Red Hat engineer will fix it immediately. They're buying the enterprise support channel.
Then there's the really elegant strategy of dual licensing.
With this model, a company offers the same product under two licenses. Version A is the free copyleft GPL. Version B is a proprietary restrictive license. If a business needs to build that software into their own closed-source product, they can just buy the proprietary license and not have to worry about the GPL's rules. It's a huge income stream.
And how do they make money from the cloud, where the AGPL is trying to regulate things?
Through the SaaS model. They host the open source application like a CRM or a CMS, and they charge customers based on usage. They're selling the convenience, the maintenance, the security of a hosted solution, not the code itself. The fact that the code is open source is actually a trust factor for the customer.
And finally, custom extensions.
This is just bespoke development. A customer pays a company to build a unique feature they need for their business. Then the customer decides, do we contribute this back to the main project, or do we keep it private for a competitive advantage?
This financial model proves that Linux isn't just a hobby. It's a global commercial force, which brings us to its role in the industry and the tools you need to control that power and secure your own data.
We've really established that Linux is the most important OS for servers and infrastructure. But when people first hear about it, they still picture those green text screens from the 1980s. We need to clear up what the user experience is actually like.
It's a really outdated myth that Linux is only text-based. Our sources confirm it fully supports both interfaces, and you just choose which one you need for the task at hand.
The GUI, the graphical user interface, gives you everything you're used to. Windows, icons, menus, a mouse. This is all handled by powerful desktop environments like GNOME or KDE. And Linux desktops are super customizable and often very lightweight, so they're great for reviving older hardware.
But the administrator's real power tool is the CLI, the command line interface.
Oh, absolutely. The CLI, which you access in a terminal, is fast, it's repeatable, you can script it, and it's incredibly resource efficient. It's a necessary skill for any power user. And here's a quick tip. If your graphical desktop ever freezes, Linux has the virtual TTY. You press key or Alt plus Alt and a function key like F3, and it drops you into a direct text console, complete to bypassing the broken graphics so you can fix the system.
Given that power, it's clear why knowing Linux is now a non-negotiable skill across the entire tech industry.
Linux skills are absolutely career essential. I mean, if you're going into DevOps, networking, cybersecurity, embedded systems, or especially cloud management, you just have to understand the Linux command line, its configuration, and its security model.
Let's focus on its role in the cloud. We need to detail the three main cloud service models, which are defined by what the provider manages versus what you, the client, manage.
Right. The cloud is all about layers of abstraction. The lowest level is IaaS, or Infrastructure as a Service. This is where you're just renting the raw computing resources, virtual machines, networks, storage. The provider gives you the virtual hardware, and you are responsible for the operating system and everything on top of it.
So that's where you're choosing your Linux distribution to install on that virtual machine.
Exactly. Those VMs are managed by a piece of software called a hypervisor.
Moving up the stack, we get to PACE.
Platform as a Service. This is the middle tier. Here, you're renting a ready-made platform that's designed to run your application code. The provider handles the OS, the scaling, all the underlying infrastructure. You just focus on your code.
And the highest, most abstracted layer.
That's SaaS, Software as a Service. You're just subscribing to use the software like a CRM or email. The provider handles absolutely everything.
The hypervisor is critical for IS, and surprise, open source dominates there too. Why are certain hypervisors preferred in the cloud?
Well, there are a few key players. Exxon was one of the early, really influential ones. VirtualBox is popular for personal desktop virtualization because it's so easy to use.
But the one that really powers the modern cloud is KVM. Why is KVM so often preferred over eggs by the big providers?
KVM stands for Kernel-Based Virtual Machine, and its big advantage is that it is native to the Linux kernel. It was merged directly into the core code, so it doesn't run as an external program. This direct integration means much lower overhead, higher performance, and better stability, all things that are essential when you're managing millions of VMs at once.
And for organizations that don't want to use Amazon or Google, but they want the benefits of a cloud internally?
That is the world of OpenStack. OpenStack is this massive, complex, open-source project for building and managing your own private IaaS clouds. It gives you the tools to manage huge pools of computing, storage, and networking inside your own data centers.
Our final segment brings this all back to the personal user and the huge importance of privacy and encryption. Linux gives you the tools, but you have to understand the risks.
The reality is, personal data collection and online tracking are just everywhere. And we have to be aware that the basic tools people think are protecting them often provide a false sense of security.
You're talking about things like Do Not Track and private browsing windows.
Right. A private browsing window only limits local tracking. It stops your history and cookies from being saved on that one computer. It does absolutely nothing to hide your IP address or stop the websites you visit from tracking you. And DNT is just a polite request sent to a website asking it not to track you.
And there's no law saying they have to listen.
None at all. So its effectiveness is minimal at best.
So for real protection, we have to turn to the hard tools of security, starting with encryption.
Encryption is just the mathematical method for protecting data. We see it every day with TLS HTTPS, that's the little lock icon in your browser. That's essential for protecting data in transit as it moves from your computer to the server.
But protecting data at rest, the files sitting on your hard drive, is just as important. And Linux offers two very different methods for disk encryption with important trade-offs.
The first is stacked file system encryption, like ECFS. This works on top of your existing file system. When you save a file, it gets encrypted before it's stored. The benefit is that it's easy and flexible. You can encrypt just one single folder if you want.
What's the security trade-off for that convenience?
With the ECFS, even though the file contents are scrambled, the metadata, the file structure, the number of files, the rough sizes can still be visible. An attacker could still learn a lot from that.
So the much stronger method is needed for total concealment.
And that is block device encryption, which in Linux is done with dmcrypt-LUKS. This works below the file system layer. It encrypts the entire disk or partition before the file system even touches the data.
So what does a block encrypted drive look like if an attacker gets their hands on it?
When it's offline, the entire thing just looks like a continuous stream of random, meaningless data. Everything is hidden. The file contents, the file names, the metadata is a bit more complex to set up, but this is the standard for full disk encryption in any high-security environment.
And the final security tip, the simplest one that people still ignore, but would probably stop 90% of account takeovers.
Password management. The single best security practice is to stop trying to invent your own clever passwords. Use a dedicated password manager to generate and store a unique, complex, random password for every single website. That way, if one site gets breached, your important accounts like your bank and email are still totally secure because that stolen password is useless everywhere else. #AppCheckOutro.
Wow, that was a comprehensive tour, really synthesizing the complexity of the whole Linux world. We went from the core definition of Linux as just the kernel to how it combines with the GNU tools to form a complete distribution. We've seen it everywhere, from tiny embedded systems to the giant engines of the cloud, often running on open source hypervisors like KVM.
And we didn't just cover the tech, we really got into the philosophy. We clarified that free really means freedom, and that freedom is protected by licenses that enable things like the fork, which we saw with Nextcloud. We broke down the business models, showing that open source is a massive commercial success built on selling support and services, not the code itself.
We spent a good amount of time on the evolution of those protections, especially that jump from GPLv2 to GPLv3, which was a direct response to new threats like hardware lockdown, that whole anti-titization thing.
And that evolution, that constant legal arms race to protect user freedom, brings us to our final provocative thought. The licensing structure from the GPL to the network-aware AGPL is always trying to catch up to technology. So now, consider the explosion of generative AI and machine learning models today. These models are trained on huge data sets that contain open source code and content licensed under things like the GPL and Creative Commons. So the fundamental question becomes, if an AI model learns from code that's governed by a copyleft license like the GPL, is the new code that model generates a derivative work? Does the AI model itself become subject to that share-alike condition?
This is a huge, immediate, and completely unresolved legal and philosophical challenge. The debate over whether an AI's output inherits the license obligations of its training data that's going to define the future of digital freedom. It forces us to ask, how do you enforce the four freedoms when the developer is no longer a person but an opaque proprietary algorithm?
That is the next great battleground for open source.
It really is. A truly challenging thought to leave you with. Thank you for joining us for the deep dive. We hope this knowledge empowers you to better navigate and maybe even influence that digital future. We'll see you next time.